So before we jump into attractor points, which is kind of the next heading, I want to go over a couple of other ways that we can go through grafting and flattening lists and series in Grasshopper. The first of which, this is just the setup we had last week where we were creating a grid of points. The first is just by right-clicking on the component output that you want to flatten, graft, reverse, simplify, whatever. You can just right-click it and reverse it. Grafting it does the same thing. So if you go in and just right-click, it brings up the context menu, graft, and ungraft like that. The other one is a path mapper. Which is a stupid little box. But the path mapper is going to let us create a mapping for any of the basic commands, as well as you can edit it to change the way that the paths work within Grasshopper. I'm just going to use the default graph mapping, and I'm going to plug the graph map in. And this guy works by taking lists A and B and then putting them into their own individual sublists. Then you can come in here and begin to edit this and play with it a little bit as you change it. Flatten it, it's taking it from two lists into a single list, and so on. This is the path mapper. And it will not bring up that context menu unless you have it plugged into something that has a valid list for it to use. All right, so Grasshopper gives you a lot of tools that you can use within Rhino as far as relationships go. The first one that we're going to work with today is an attractor point. So this is going to let us control a geometry or a transformation based on proximity to a specific point in Rhino. So the first thing that I'm going to do is I'm going to make a square grid. And it's going to ask us for a plane, a base plane, a size, which is going to be the size of each cell. And because it's a square, it's going to have the same length on either side. The number of cells in the x direction and the number of cells in the y direction. So I'm just going to come up with a couple of sliders. I'm going to copy the ones down from up there. And I'm going to let that go to 0, but I'm going to make my grid much larger. Or 1, I'm sorry. So we have this rectangular grid with the base plane showing. And we're going to do a couple of things with that. I'm going to go ahead and flatten this list of points so that they're all in the same list instead of each vertex being its own list. So what it's not going to show us at the moment is that each of these points, there you go, each point, each vertex of the square grid is being pulled out as a point, and then the cells are being pulled out as square curves. So I'm going to create a set of polygons centered on each of these vertices. And I'm going to do that with just a plain old polygon command, a radius, a number of segments, and we'll make them triangles. Then I'm going to take my points and use each of those points as a base plane. So it's going to take the XY plane from the square grid as well as the point and create a polygon around the center of each of those points. I'm going to just edit my number slider so that I can make those a little bit smaller by dropping it from the integers into the real numbers. I'm going to turn my grid off. So what we're going to do is we are going to use these triangles and we're going to scale our polygons based on their distance to a certain point, and that point we're going to call an attractor point. So I'm going to just come into Rhino and drop a point object in there. And I am going to use a data entry. I'm going to set one point. It's going to prompt me to choose a point. All I did is I went into Rhino this time and constructed a point in Rhino. So I actually have a Rhino object that I can move around in Rhino. And I used a point data object, and I set one point and then selected the Rhino geometry. Does everyone follow? Sure thing. So I created a point in Rhino, which is this guy right here. I created a data point. Oh. So instead of construct point, I used a collection of points. I brought up the context menu, set one point, and then I selected the point in Rhino. Get it? Awesome. So I'm going to use that point. I'm going to find the distance from each of these polygons to that point. And I'm going to use that distance between points to determine how much we're going to transform these other triangles by. So I'm going to use a distance command, which is a distance between 2 point coordinates. And if you recall, we used the points as our centers here, so we can make that point A. And then point B is just going to be that attractor point that we have. Now if I come over here, drop a panel in, it's going to give me the distance between each of these points and that original point that we have. So I should have 100 and something values, which I do. And each of these points numerically is going to correspond to the numerical value of the point on the panel. So we've got our set of points. We've got the distance between each point and this attractor point that we've chosen, and it'll move as we move this point around. And now I'm going to create a domain using a bounds command. So what this is going to do is it's going to take a set of numbers and it's going to create a domain that includes all of those numbers. So the lower bound of the domain will be the lowest value in the data point list. The highest or end value of the domain will be the highest point in that list. And we can bring a panel in here again just to see it. And there's our domain, 0.5 more or less to 8.5. And that will change based on how we move this point around. So the next thing I'm going to do is I'm going to remap my set of numbers. And the remap command is going to take me from one domain into another domain. So it's going to let us change the base domain for a set of numbers. It's going to ask us for the values that we want to remap, which are going to be our distance points, the source domain, which is going to be our bounds domain, and then our target domain. And that's going to be based on how much we want to scale these triangles. So I'm going to create a domain here. Remember, it's construct domain, not just domain. And I'm going to take a couple of number sliders. My domain start, well, we can't have our domain start be 0 because of how Grasshopper works. We want to be scaling these, so we don't want to be scaling by a 0 factor. And then let's make the highest point of our new domain as 2. So what I'm doing here is these are going to be the bounds for our scale command. So the smallest scaling factor we'll get is a 0.001. The largest scaling factor is a 0.2. And it's going, this remap numbers command is going to take our distance values and their relationship to their source domain, so the distance, the bounds of that list. And then it's going to remap that relation to a new domain, which we're going to then use to scale the polygons. Questions? Okay. I'm going to just drop this in here as my target domain. And then I'm going to use a scale command. Bring this guy up a little bit. Our geometry is our polygons. Our center points are going to be these original points all the way back here that we used to base the polygons around. So you can see it shifting in Rhino. We have a set of consistently scaled polygons now. And then our factor is going to be this mapped number from the remap numbers command. So now we have these variably scaled polygons based on their proximity to a point. So from the beginning of this step, we created a square grid. We defined the size of each cell and the number of cells in the grid. We then took our list of points at the grid corners and used each of those points to create a polygon. Based on those points, we found the distance between a point that we chose and the center of each polygon, or the corners of every grid cell. And we found the upper and lower limits of that list of distance numbers or values. We used those distance values to create a new domain that's more scaled for scaling, which is to say we weren't going to be scaling one of our triangles by 10 times. And with those remapped values, because the relationship is preserved between bounds and bounds and values here, we then used a scale command centered about each polygon to scale variably based on proximity to an attractor point. And you can do this with pretty much any command. We could come in here and use rotate instead if we wanted to, and we could rotate these guys. Maybe do this. Maybe we want to rotate now that we've scaled things. So we can remap another set of numbers. And this time, our new domain will let me open up and edit my panel. Curious. Our new domain is 0 to 90 because we want it in degrees. So we'll make that our target domain this time. And then if we look at a panel here, our mapped values are going to be between 0 and 90. It's going to sort them descending. It'll run through. Do that. So we have a mapped domain. We need degrees to turn into radians. That'll be our angle. Now we can rotate each of these points, but it's rotated funny because we rotated about a plane instead of about each point. We'll grab the points and drop it into the plane. So now our polygons are scaled and rotated based on a proximity to a point. We could do the same thing, we can begin to extrude these. If we wanted to extrude them in unit Z, the same value that we scaled them by, maybe. Here's our base geometry. Here's our unit vector. Yes. You can begin to play with that. I will look into why that didn't work quite like it was supposed to. Yeah, I'll look into that. But you can begin to work with an extrude command in the same way you can work with a rotate or a scale. So that's one attractor point. What happens if we want more than one? So everyone can see what's going on here, I'm just going to make my grid a little bit larger so that we have a little bit more room to see what's going on. I'm just going to drop that same guy into both so that I always have a square set of square grid points. So I've got all of these triangles, and with the 1 point I can drag it around and change it as much as I want. But I can also do the same thing, here are my polygons, with 2 points. So I'm going to drop another point, or 3, in Rhino. I'm going to come down here and give myself another points set. And this time I'm going to bring it up and set multiple points. And I'm just going to select all 3 of these points. And now each of these points is mapped to the point command. So the next component that I'm going to use is going to be a closest points. It's going to ask us for the points that we want to search from and the cloud of points that we want to search. So our points here, the ones that we set, are going to be our cloud. They're the ones that we're going to search based off of. But our points from our square grid are going to be the points that we are searching out of. And this distance is going to give us the distance from every vertex of the square grid to the closest of those defined points in Rhino. And we can do the same thing we did before. We can set up a bounds, and we can create a domain. Oops. I'm just going to let it be the same domain that we used before. And then we're going to remap the numbers again. Because right now, we'd be scaling variably from 0.35 to 11.5. And scaling any one of those triangles by 11.5, we can do, but it's going to be kind of crazy. So just to show you what happens when we don't remap anything, you plug our polygons into our geometries, our points into our centers, then I'm just going to plug this domain into the factor. It works, but you can't see what's going on there. So we're going to remap our values out of the closest points, our source domain, and then our target domain. That'll give us a little bit more reasonable set of scaling factors. And you can, again, just begin to move these points around. Questions? All right, so the same kind of thing that we can do with a set of points, we can do with a set of curves as well. But the trick about the curves is that we're not actually going to do it with curves. We're going to do it with points that we place on a curve. So, there's our grid again. And I'm going to come over into Rhino and I am going to draw a curve. It'll be some funky curve that I like this morning. We've got a curve in Rhino. And we're going to bring it into Grasshopper just like we brought the points in, just like we can bring surfaces in. It's just going to be a curve. A collection of generic curves from Rhino can be represented in Grasshopper. And I'm going to do the same thing I did before and set one curve, have it selected, and now we have a curve that's being referenced from Rhino into Grasshopper. So just like if we were in Rhino, we could divide a curve into a number of segments, right? So we've now got a bunch of points on our curve. We can do the same thing in Grasshopper. We can do divide curve, and it will divide it into an equal length segments. So we'll give it our curve. We'll give it a count. We'll let it go up to 10. And we're just going to let the kinks be false. We don't need it to. We want it to be a smooth curve. So we'd have put a set of points. There are 10 of them. Change that. The more points you have on the curve for this kind of problem, the smoother the attractor curve is going to be, because the attractor points are going to reference these points, not the actual curve itself. So I'm going to use the closest point again, along with our set of points that are our cloud, and our points from our grid way back up here as the points to search. And the same thing, we'll use the distance to create a set of bounds. We'll construct a domain, and we will remap the numbers with respect to their source domain to a target domain that's more suited to scale. Because again, scaling by 11 times is going to get ugly and messy fast. We'll use our scale command. We have a factor. Our center is our points again. I plugged it into the right place. And then our polygons are our geometry. If we turn the polygons off up here, you can see what's going on. So we're scaling just like we did with the other examples with respect to the position of this curve in our field of points and polygons. Does that make sense? Okay. So using attractor points like this are going to let you have a little bit more control over a specific surface. I've talked to a couple people about using this kind of thing in studio projects. Used it in studio projects. And it lets you begin to work in 3 dimensions as well. Like I said, you can do a Z move and start to bring things up or down and then loft between the Z moves. Extrude based on a distance that so the next thing that we're going to do is take a little bit of time to look into populating a surface. And there are a couple of ways to do this. But the first thing that we're going to do is just build a surface that we like in Rhino. So I'm going to minimize Grasshopper for a few minutes. And I'm just going to make a plane. Let me drop this into shaded so you can actually see what I'm doing. And points on. I'm just going to start to move these points around and edit the plane curvature. And start to create some sort of surface. It doesn't really matter what yours looks like, it can look like anything. But what we're going to do is now in Grasshopper, I've got a plane of some sort. I could make it a curve if we really wanted to. We could take this curve that we have, copy it over, rotate it in 3 dimensions, and then extrude it. Maybe that's a little bit more interesting. We can begin to play with that and turn our points on, start to edit these points, which aren't going to give me a whole lot of options. But anyhow, we can populate a surface with points in a couple of different ways. So the first is with a popgeo command, is populate geometry. It's going to ask us for an input geometry, and I'm going to use a surface point to bring in a single surface. That's an extrusion, so I have to explode our extrusion to create a surface. So now we've got a surface. And I'm just going to hide it in Rhino so it's not in the way of what we're doing with Grasshopper. So we have our geometry, and it gives us a default count, which is 100, and a default seed, 0 or 1. But it doesn't really matter how many points we use. Just note that these points aren't organized in any shape. They're not gridded, they're not banded, they're just populated on the surface. That's potentially useful, but maybe not as useful for anything that we would want to do where we have a gridded surface population. So I'm going to take this surface, and I'm going to do pretty much the same thing. I'm going to take a geometry in, that one geometry, and I'm going to hide it in Rhino again, just so it's not in the way of what we're doing. You can see it's a smooth surface in Grasshopper. I'm going to subdivide a surface. And the abbreviation is S-divide, but it's divide surface. We have a surface input, and now it is a gridded set of points placed onto the surface. I'm going to ask for a count value, and I'm just going to grab a slider, and I'm going to say we want the same number in both directions, but maybe not 100. Drop it back down to 10. So the divide surface is going to divide it in a regular manner. The populate geometry is just going to populate it with a set of points. So I'm going to come over here, and I'm going to create a geometry in Rhino. And I'm just going to make it a circle. Nothing too crazy. Maybe a radius of 1 or diameter of 1. And I'm going to make it a surface. And I'm going to use that surface as a geometry in Grasshopper. And for this, I'm going to actually move this guy back over to the origin. I'm going to convince Grasshopper or Rhino to snap to the center. I'm going to use the point to move to just a 0, 0, 0. So our Grasshopper and our Rhino geometry came over to the origin. I'm going to then construct a point. Just let that be the origin itself. And I'm going to create a set of vectors that are going to end up functioning as movement vectors. But I'm going to begin to take this circle disk that we've created, and I'm going to move it to each one of these points on our surface. I'm going to show everything in Rhino and just move this over so we can see what we're doing a little bit better. So our vector 2 points, we want our endpoint to be the points that we've subdivided, right? Because that's where we want our moved geometry to end up based on these movement vectors. And then we want the base of the geometry to be our origination vector point, because we want to take that base geometry to the points. So that just happens to be the origin here. So if we turn our vector previews on, we can see that we have the set of vectors moving to every point. The vector display is just asking for an anchor point to base your vectors from, and that's going to be your base point for your vectors. We've got that, and then we're going to use a move command. And our geometry, remember, is our circle. And our motion is a set of vectors. So now we have these circles at every point on our surface. I might come over here and just scale our circle a little bit so we can see what's going on. And it just increased the size of every one of those disks. So we've now populated a curved surface with these circles based on a division of points. And we could also do the same thing with this populate geometry, but it's going to be a randomized spread. So if we wanted to do that, we could use our surface geometry. I'm going to hide this stuff really fast. And do the same thing. We can actually just use the same point, but a vector between 2 points. The population is a set of points, so that's going to be our point B. Our base point is our point A. And then our move takes the geometry, which is our circle, based on the vectors. So we have this random set of points now on the surface. But I'm going to choose instead to work with this set. And we're going to do the same thing before. We're going to use a single attractor point to scale these guys. So maybe our point up here, or down there rather. I'm just going to move the point vertically so that it's closer to the surface. So that'll be our point. We can bring it into Grasshopper. By having the point selected in Rhino, when you go in to set a point, it's going to automatically select that point instead of having to click in or select each one in the selection window. We're going to do the exact same thing we did before. Distance between 2 points. We're going to take our A set as our subdivided points and B as our selected point. Remap the bounds. And then I'm just going to come up here again and copy our domain construction and our remap from before. So our source domain is going to be our subdivided our source domain is our distance. Our values are our distance points. The target domain is our constructed domain. And then we can scale just like we did before. Our geometry is way back here from our movement. Our centers are these sets of points. And our factor is our remapped. So if we turn off the move, we can see it's scaling based on proximity to this point. And if we move it again closer to the surface, it'll start to change how that reacts right there. We can change our base so that it's visible all the way through and play with that a little bit. Now that we've scaled it, let's say that we want to make these discs level with the surface where they intersect instead of being just stepped like this. So we can use a plane normal. Let me go ahead and just group this stuff. We can use a plane normal. We can use the plane normal to take our origin and our relative z-axis. So when we looked at our divide surfaces, it gave us a set of points and it gave us a set of normals. Remember, the normal vector is just perpendicular to the surface at that given point. So our normal vectors that are perpendicular to our surface are going to be our z-axis. I'm going to flatten them. And our origin will be our points. So the origin is going to be the base for each of the normal planes. Flatten our points as well. So that's a little bit messy, but you can see now at every point a normal plane, and Grasshopper shows these planes as the gridded constructs there. They're not actually Grasshopper objects. So Grasshopper has generated a plane that is parallel to the surface at a point so that the normal vector, the vector perpendicular to the plane, will be the same for the surface as it is for the plane. So we can then rotate 1 and 2 our scaled geometries about this plane set. We turn off our planes, scales. You can see now that we've rotated all of these disks to lie in plane with the normal planes of the surface. So we can do something a little bit different and a little bit fun now. Let me pull up my colors. So what we're going to do is I'm going to give you guys this Grasshopper script. This script is from Rachel, and it is going to let us render colors, a color gradient, into a Rhino file from Grasshopper. So I'm going to use this set of rotated disks. I'm going to hide our base geometry. And we have a set here. So I'm going to use these guys to change the color of our geometry. So we have our, need to get my edges out. We have our geometries, and I'm going to give you all this file so that you have the setup. It shows you how we're going to plug everything in. You can use it for your homework set. But I'm going to use geometries that we just created and a boundary surface to create this. And then go through And I'm going to find the center of all of my polygons. Technically, circle isn't a polygon. A little bit unfortunate. We'll just use this. So we've got a polygon set, and we've moved them, and those are these guys right here. And then we found our boundary surfaces, so we just created a surface between them. And our point has vanished previously, so I'm going to just set a point. This is the attractor point setup, remember. The distance between the centers and a point, the boundaries. You're not going to have to recreate any of this. I just want to talk you all through it. And then we're deconstructing the domain. So we're taking the boundaries and getting the high and the low, and then using that on our color slider here. And if we turn that on, our preview is going to show us our color gradient. You can start to play with the color gradient here. And Grasshopper's color gradients are a little bit finicky. Sometimes you can get them to go away, sometimes you can't. But you can begin to play with your color gradient. And then this script set is going to just bake it with those color attributes. So all you have to do once you get this set up is toggle. This is a Boolean toggle right here. You just have to double click on it. And then it will bake your geometries. And it will show in the shaded view. Wireframe, it's baking it based on a material attribute. And it will show in rendered. So it's setting, Grasshopper is setting the render materials as well as changing the layers that it is baking it to. So it's on this gradient layer that Grasshopper has written into Rhino. All right, does anyone have any questions about this, about anything we've done thus far in the semester, about any of the homeworks we've done? You should be able to. We can try that. Let me come back over here. So you're saying that maybe we use our base geometry back here instead of, there we go, a surface, correct? All right. Then we can just take that geometry and find the center of it, aesthetically. I don't know. We're about to find out, is the short answer. I'll set one point. Well, it's orange. No, I will ask Rachel about that because there is a way to do it. I just don't know quite how she has written the script. Because what it's doing basically is it's taking the distance between each of these points. Right now there's only one point. So we could maybe use a command point setup like we have here and find the bounds and deconstruct those and begin to, no, not quite. It's green now. So progress. But basically what this is doing is it's taking our points and it's, actually, we're not done yet because it's found the distance here. We can take our just plain old distance maybe and put it in for our target. No, I'll ask Rachel about that. Hypothetically, there is a way, but pretty much what this is doing is it's using the control points to define the gradient. And you saw over here, the gradient is consistent across each shape. So it's actually changing the gradient across the shape. It's hard to get a gradient in Rhino across a single surface, but I will ask her if there is a way to do that. But it's green. I don't know how I made it orange before, but we'll see. All right. Other questions? And I will put this file that we're working through in class along with the summary of all of the commands that are in the file off to one side. You can see that's going on over here, as well as the color script file on on Canvas. But assignment 4 is on Canvas. And it's going to be asking you to use the attractor points to create a field. And this is pretty much what we did in class at the very beginning, the scalar change based on multiple attractor points. A rotational change, an extrusion height change based on a curve. So it's asking you to start layering these things. And then the gradient color change based on a single attractor point. And that last point will work out very much, undelete my colors, like it did for, we've got these geometries which are definitely not polygons, but we can fix that. I'm just going to make a square. Based on a center, which is going to go at 0, 0, 0, with a length of 1 and a length of 1. So all I'm doing here is just going, oh dear, it's not what I wanted to do. Going back in here and turning all of these things to squares instead, so that I can begin to have geometries that are actually square and therefore have centers. Then we can take this distance, and our bounds are based off of that as well. And now we have a gradient for those multiple ones. So you're going to use this color script to set up that last step of the assignment. And then other than that, just remember to answer the lecture questions. And there are a couple of precedent examples of what, your fields might be rectangles. This one looks like it's based off of a curve, right? Maybe there are a couple of smaller secondary curves going on in here. And a rotational change, extrusion heights, and then a color gradient. So there are all sorts of different ways you can use this. think, Mariel, did you get your studio project figured out to some extent? Okay. The extrusions, do you mind if I talk about your project?
Yeah.
So Mariel's studio project is looking at negative space and changing the extrusion height of stacked squares. So that grid set, changing the three-dimensional height of those squares and then lofting between them or extruding between them is how I would maybe go about pushing forward with that. I didn't want to tell you that over email because I'm ready to do it in class. But so you can start to play with that. And the biggest thing is make sure that your points are in Rhino, not in Grasshopper, so you can move them around easily. And I'll put this up on Canvas so that you can follow along. It gets kind of messy kind of quickly. But questions, comments? Otherwise, if no one has any questions, we will call it a day early.